Hey there, it's Chem Coach Powers, and today we're going to be talking about chemical reactions. Finally putting together all this stuff that we've been building on for the entire semester, putting it into what we call a chemical reaction, right? So things are going to be clicking and making sense even more than ever as we get going here today. So let's go ahead and get rolling. We're going to describe chemical reactions with these objectives here. This is from section 8.1. Identify the characteristics of a chemical reaction and list observations that suggest that a chemical reaction has occurred. Identify the parts of and interpret the notation used in chemical equations, and relate the conservation of mass to the rearrangement of atoms in a chemical equation. And finally, to write and interpret a balanced chemical equation for chemical reactions. We're going to do some balancing. Now, a lot of this stuff is review for you guys because you did this in physical science. Let's look at what we want to walk out of here with. What is our criteria for success? When you observe a chemical reaction, or given the observation descriptions, you would be able to identify the evidence that indicates that the chemical change has occurred. You should be able to identify the reactants, the products, the states of matter, and other common symbols that are used in chemical equations. Given a word equation, you can write a formula equation, and vice versa, formula to word. You can use the law of conservation of mass to explain why equations must be balanced. And of course, you can use coefficients to balance equations. All right, so let's get into this. Chemical reaction, what is it? It's a process by which one or more substances are changed into one or more different substances. So the products are going to be different than the reactants, and they're going to have different physical and chemical properties, okay? Now, something is absorbed or released. What do you think that is? What do you think is going to be absorbed or released? Well, it's going to be the energy, right? Energy is going to be absorbed or released in a chemical reactions. But what is conserved? Mass. Mass is conserved. You're going to have the same amount of mass before and afterwards, and that's going to lead us into balancing chemical equations, right? So your reactants are turning into your products. Your reactants are typically on the left side, products are on the right side, but those can flip, especially if we talk about equilibrium equations, right, where it goes in either direction. So the original substances are going to result in a new substance. What kind of evidences do we have for chemical change? Well, heat and light can be emitted. The color can change, sometimes drastically. Formation of a precipitate. Now, a precipitate is a solid, okay, that is produced in a chemical reaction. Basically, if you take two clear solutions, you put them together, and all of a sudden this cloudy substance occurs. It's going to be a solid. If you evaporate out all the water, it's going to be left with this solid that's there. And that is going to be one of the evidences. And you also have production of gas being one of the evidences of a chemical change. All right, so what kind of characteristics do we have of a chemical change? Well, we're going to talk about representing chemicals, right, with symbols and formulas. And we want to represent the number and types of reactants and products. Okay, so this is the number and the type of the reactants and products. We have to make sure that when we're done, we've satisfied the law of conservation of mass, that we have the same number of atoms on each side of the arrow. So for example, here you can see that I've got sodium and water reacting, and I've got two sodiums here and I've got two sodiums here, right? We have to make sure we have the same amount. I've got 4 hydrogens and I've got 2 plus 2 hydrogens. So I've got 4 hydrogens. I've got 2 waters and I've got, 2 oxygens, and I've got 2 oxygens. We have to make sure that they're the same on both sides of the equation. All right, so let's look at some of the different little symbols that we have here. What are the parts of a chemical equation? Well, remember that chemical equations are going to include the formulas for atoms or molecules or formula units. Remember, formula units are the ionic compounds, right? Molecules are the molecular or covalent compounds, right? And then, of course, you might just have an elemental material, so it might just be an element, and so you might just be talking about the atoms. So we can represent all of these different types of materials with the symbols, right? The formulas that we have. And so we have to make sure that we have the correct symbols and subscripts. As you can see here, I've got a formula unit, calcium carbonate, a molecule of hydrogen, and the atom or the element of aluminum. Remember that coefficients are I actually like to say the big whole numbers, okay, that we put in front of the formulas, right? Because I think of this little 3 there, or that little 2 there. I think of those as smaller numbers compared to a big number that I might put in front of an element, like the 2. Like that 2 and that 2 are way bigger than that one. So I like to think of the coefficients as the big numbers in front, and then the subscripts are the small numbers that follow the element. Remember that we're going to need a positive or a plus sign to indicate that we're adding these things together, all right, that they're mixed together in some way, right, that we have more than one reactant or product depending upon where it is. The arrow is just another way of representing the word yield or produces or makes, right? And so then the other thing we're going to add is the symbols. Now, the symbols are telling us the reaction conditions. That's a solid, that's a liquid, that means aqueous, which means it's dissolved in water. Okay, you can also have gas. There we go, right over there. And so you've got 4 different symbols that we can use to indicate the state of the substance that we're dealing with. Okay, so let's go ahead and go to this question here. Make sure you're understanding the formulas. How many atoms of each element are in calcium carbonate and then 4 calcium carbonates? All right, why don't you, actually, I'm going to go ahead and open up those next 2. Why don't you pause and practice this real quick? Make sure you can guess how many are in each. How many elements, okay? How many, not different types of elements, but how many atoms of each element are in each of these? Okay, pause and practice. And we're back. And what we've got here, we've got 1 calcium, 1 carbon, 3 oxygens. But here we've got 4 calciums, 4 carbons, and 12 oxygens. Here we've got 1 aluminum, and we've got 3 nitrogen and 9 oxygens, right? 3 times 3 for oxygen. But here we've got 5 aluminum, and then we've got 3 times 5 of my nitrogen, so that's 15. And then I've got 9 times 5 of my oxygen, so I'm actually at 45, okay? So you have to multiply the subscripts through anything that's in the parentheses, and then that coefficient is going to multiply through everything in the entire molecule and or compound, the formula unit. So here's a basic table that kind of summarizes a lot of the things that we need to know. A couple things that I haven't showed you yet. This double arrow means that reaction can go in both directions. Oftentimes we use this with equilibrium reactions. This is a reversible reaction. Okay, we also use symbols like a triangle or heat to tell you that this reaction actually needs heat in order to progress, that the reaction won't take place unless we add heat to it. And then sometimes we'll use things like these little element symbols like palladium or platinum above the arrow to indicate, you know what? We actually have a catalyst in this reaction, and that catalyst is something that you need in order for this reaction to speed up. And so the reaction will take place with platinum, for instance. All right, so if we take a word and we take this sentence and we put that sentence out there, you should be able to write a chemical formula for that, okay? So I can say this is a reaction description in a sentence format, right? This is kind of like in a sentence. And so I can say the solid sodium hydroxide reacts with liquid water to form aqueous sodium hydroxide. I would expect you to be able to take that and turn it into solid sodium oxide is going to react with liquid water, H2O with a little L, right? Sometimes I use a little cursive L, to give you or to form aqueous sodium hydroxide. And it says it's aqueous, so we got to put that on there. And then we were going to have to, if we wanted to balance this, we'd have to put a 2 in front of that to make sure this whole thing was balanced. But this is what I would expect you to be able to do, okay? You can also take that and put it into a word equation. This is a little bit more, simplified, where we just put the names and then we can use arrows and we can use the plus sign. But really, we're going to be asking you, if I want a description or a word description, I want this one up here. Yeah, this one's just a little too simplified. And then, of course, what I told you is you need to be able to do this, right? You need to be able to take the words and turn it into this. But you should also be able to take this and turn it back into the words, right? So you should be able to go both directions. All right. Now, one of the things I want you to be able to recognize is Brinkelhoff. Brinkelhoff is this little phrase that we use, that should be a little BR there. That little phrase is what you are going to remember for the rest of the year. If you hear me say Brinkelhoff, you know that I am talking about these 7 different diatomic elements. And what this means is that anytime we represent any of these elements, like bromine, in a formula, in a chemical reaction, I'm never going to say Br. I'm always going to say Br2. Now, the reason for that is because these are all diatomic elements that in their natural state, they're always going to combine with each other and form pairs. Okay, so we know that Brinkelhoff is made up of a bunch of different elements that, and you'll notice pretty much all of these have 7 valence electrons except for hydrogen, oxygen, nitrogen, but they all will form these bonds, right, where they're sharing these electrons, right? And so that's not meant to indicate a double bond there. You're going to end up having pairs of all of these, okay? So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine all will form bonds with, and those bonds are going to be with each other. And so that's why they're always forming these diatomic elements, okay? So if you ever see nitrogen for the rest of the year, you're going to be like, oh, well, nitrogen forms that triple bond. I remember that, right? Nitrogen forms that triple bond. And so I've got to remember that nitrogen is always N2, and it's never just N by itself. Now, something like aluminum is going to be by itself, okay? But nitrogen is not going to be by itself. It's going to have a little 2 after it. So all of these Brinkelhoffs, okay, all of those elements there, just remember Brinkelhoff, those will always be diatomic. All right, so you should be able to now write a formula equation for these. So if I took and I asked you to say, to take solid magnesium and react it with oxygen gas to form solid magnesium oxide, you should be able to do that, right? All right, so what would that look like? Well, I'm going to have you practice that one, and we'll come back. Ready? Pause and practice. Boop. And you're back. And this is what you should have gotten, okay? Mg with a little S after it plus O2 with a little G gives you MgO with an S after it. Let's try the next one. Carbon monoxide plus chlorine gives you carbon tetrachloride plus oxygen. What would that look like? Pause and practice. Boop. And you're back. And you should have had CO plus Cl2 gives you CCl4 plus O2. Now, notice I don't have any of my states of matter on this one. I don't have my little G after this, for instance. Well, I didn't tell you that carbon monoxide was a gas, right? And so that's why you didn't have to put it in here. Now, I would expect you to know that carbon monoxide is a gas. And so if I asked you to put the states of matter on this one, you should be able to do that. Why? Because chlorine, you know, is a gas as well, right? Why on the periodic table? It's actually a different color, and that indicates that it's a gas, right? I wouldn't expect you to know carbon tetrachloride necessarily, but I would expect you to know oxygen gas. So I would expect you to know 3 out of the 4 of these were actually gases, just from your prior knowledge. Then I could expect you to also write a word equation for something like this. N2 plus O2 gives you N2O. What would that look like? Well, again, I haven't given you states of matter here, and so I wouldn't necessarily expect you to know this one, but I would probably expect you to know those 2, because those are both parts of the air that we breathe, right? So you could say nitrogen gas. Now, one of the things that we could do also is we could add even more information to this. If this is a balanced chemical equation, and it's not right here, if we put a 2 in front of that and a 2 in front of that, now it's balanced, you could say something like 2 moles of nitrogen gas reacts with 1 mole of oxygen gas to yield 2 moles of dinitrogen monoxide. Whoops. Okay. Now, I don't need you to say that that's a gas, even though I hope you probably could figure out that it would be, because it's a non-metal combination. But if you could do this, that's exactly what you need to do for a test. Okay, I wouldn't expect any more than that, but I would expect you to be able to do that much. All right, chemical reaction demonstrations. Well, there are a couple video links that you can look at if you'd like. You can type these in and watch them to see what these reactions are like. If you have the slide, you can, and you're looking at the slide itself, then you can click on these links and you can go watch those. But basically, magnesium and oxygen are going to react and form a bright light as you burn it in the presence of heat. Copper 2 chloride and sodium hydroxide are going to form a solid precipitate. It's going to form a little white, or it's going to look bluish because it's in a copper 2 chloride solution, which is blue. And that's going to be a little bluish kind of precipitate. This is simply propane burning in the presence of oxygen. Okay. And then this last one is hydrogen peroxide. This link down here you want to watch if you guys like David Dobrik. This was at one point the largest elephant's toothpaste reaction ever done. There have been some bigger ones, but this is still my favorite. It kind of looks the best, I think. Fills up his entire backyard almost instantaneously. It's really cool. Anyway, so those you guys can check out online. Got some videos for you to watch there. But I would also expect you to be able to take those reactions, okay? And you can see magnesium plus oxygen. I'd want you to be able to take those words and put them into formulas, right? So magnesium plus oxygen. I'd want you to be able to write the chemical equations for these. And you're going to have to do this for the lab that we're doing as well. So Mg plus O2. You are also going to have to try to predict what your products are. And this is what we're going to be practicing not only for this lecture, but also in the next lecture. You need to try to predict what are these things going to do when they combine. And sometimes that's a little bit tricky, but I'll go ahead and go through these and help you out a little bit. This one is copper 2 chloride reacting with the sodium hydroxide, right? So that's what you saw here in this reaction. And you need to be able to put that into a chemical symbol. So there it is. The propanol, right, was, in this case, you might not have, I would not expect you to know 2-propanol. We haven't learned that yet, okay? So you should be able to do all these others: magnesium, oxygen, copper 2 chloride, sodium hydroxide, oxygen. And this last one, I would expect you to know hydrogen peroxide, but I would not expect you to know 2-propanol, okay? That's organic chemistry naming, and we haven't learned that yet. So, but you should be able to try to predict the products still, right? And we're going to learn about how to predict these products here in the next lecture. So I'm not going to jump into this right now and really go into detail, because we'll go into that in more detail later. But basically, this is going to be magnesium oxide, okay? And then we could balance that. This is going to be swapping partners. So you're going to have copper hydroxide plus sodium chloride. This one is going to be carbon dioxide and water. And you might be like, how in the world do you know that? They're really easy in this case. And then this is a reaction in where you're just going to get hydrogen gas and oxygen gas. So, this is H2O plus O2. All right. All right. So let's look at balancing chemical equations. Like I said, we'll get into that next chapter or next unit, 8.2. But for now, let's just hit chemical equations, and then we'll go all into that stuff later, and you can do that for your lab. So if I look at this scenario, I've got sodium plus chlorine gives me sodium chloride. And I look here, I've got a problem with the scenario. Why? Because my chlorine is not following the law of the conservation of mass. I've got 2 chlorines on one side and only 1 chlorine on the other side. And that's not okay, because it's got to follow the law of conservation of mass. So what we do is we balance chemical equations. And again, I know many of you guys did this in physical science. So it's going to be really easy. It's going to be review, and it's a lot of fun. I know if you're like me, you like to balance equations. So it's going to be necessary to balance these equations to make sure that they obey the law of conservation of mass. Now, what we can do is we can add entire molecules or compounds, formula units of things, but we can't change subscripts, okay? We're always going to balance using coefficients like that, put that 2 in front here, but we're never going to change we're never going to change subscripts, right? So I cannot put a 2 down here by the sodium underneath it. I cannot change it and make it subscript, but I can change the coefficient, okay? So always balance with coefficients. So how do you do it? What are the steps? They're pretty easy. You just basically write the formula equation if we don't give it to you. So you actually write out the formula, right? That's like we talked about here briefly. And then we're going to adjust the coefficients after we've counted the atoms. You got to count up the number of atoms in each side to see how many they are. I really suggest that you do this step. Some kids like to just skip this step and go and just start balancing without doing this step. But I will tell you that this step will save you on those more difficult problems. Remember that this is a back and forth situation. There's a lot of trial and error. I would suggest that you just start with the elements that you see first, or the ones that are only present once on each side. And I would suggest a lot of times that you do the hydrogens and oxygens last, especially the oxygens last. That usually helps. Keep the polyatomic ions. Maybe you have something like a sulfate. If they're present on both sides, keep them together in a group. Okay, don't break it up into sulfurs and oxygens. Just keep that together as a sulfate, and that will make it a lot easier for you. And then double check when you're done. Always check your work. Make sure you got it right at the end, because if not, then you miss the whole question. So I like to bring this into 3 really easy steps, all right? 1, balance one element at a time. 2, if you accidentally unbalance an element, don't panic. It's okay. Leave it alone. You're going to get it in the next pass. You're just going to make successive passes. So I want to show you an example of this. Sorry, it's a little hard to see, but we got Al2O3 plus carbon gives you aluminum plus carbon dioxide. Okay, so is it balanced? Well, let's just kind of count up what we have on each side. And what I like to do is I like to just kind of write them out. And I say, okay, I've got aluminum on this side. I've got 2. On this side, my aluminums are 1. Okay, I put little equal signs here. My oxygens on this side are 3. My oxygens on this side are 2. My carbons on this side are 1. My carbons on this side are 1. So you can see that my carbons are already balanced. Sweet. My oxygens are not. Oh, no. My aluminums are not. Oh, no. That's okay. Okay, so this is what we do. Count them up first on each side. And in this case, we're going to give you a visual representation of that. You can kind of see what they look like. You can see there's 2 of the aluminums on the left and 1 on the right, et cetera, et cetera. So what do we do to change these? Well, we just have to change our coefficients. And so the first thing I would do is I would start with my aluminums, right? And I'd say, well, that's the first thing I see. And I can easily put something in there to balance it. So let's just start with the aluminums. Let's throw a 2 in front of that and see what that does. So when we do that, we can see now that our aluminums are balanced. Yay. Our carbons are still balanced. Yay. But our oxygens are not. So we still have one more thing to balance. So we look at the oxygens. It's okay. Remember, we said to balance the oxygens last. And here I've got 3 oxygens, and here I've got 2 oxygens. So one of the things you want to do is you want to think when you have something like this, where there's just 2 instances, 1 on each side, but they have different numbers. Think about what the least common multiple would be. The least common multiple of 2 and 3 is 6. So let me make this a 6. How do I do that? Well, I can put a 2 in front of that, and I can put a 3 in front of that. And now I'm going to have my oxygens balanced. So let's do that. Boom, boom. Now let's look at them. Now this is where you're like, oh no, I panic. I cannot believe I just unbalanced my reactions. No, that's not the case, right? We're not going to panic. Why? Because we were told not to, that's part of our rules. We don't panic. I went skip forward there. Come on now, let's get going. Come on. There we go. All right. So you'll notice that I've got my 4 aluminums now on this side and only 2 on this side. And so I've unbalanced things, but I've also unbalanced my carbons, right? Because over here now I have 3 carbons and I have 1 carbon here. And it's going to take multiple passes. Sometimes you're actually going to go past the balancing point. You're going to have to go back and reduce. But this is okay. Just don't panic. Just make another pass. And so I can see, what do I need to balance here? Well, my aluminums are not balanced, but I can change one little thing real quick here. And I could turn that into a 4 instead of a 2. And that would balance my aluminums. And then I could throw a 3 in front of that. And that would balance my carbons. So it's really not going to be too big of a deal. Throw a 3 in front of my carbon. Sweet, now my carbons are balanced. Change my 2 to a 4, and now my aluminums are balanced, and now I'm balanced. So this is the process of balancing chemical equations. It's easy and it's fun. Sometimes they're kind of crazy and hard. We have one problem that we do for extra credit some years, which can take you like almost an hour just to try and figure out how to balance. And very few students are actually even able to do it. It's kind of crazy. You're like, there's no way this could be that hard. It can be. It's kind of crazy sometimes, but most of the time it's not that hard, and it's never going to be that hard for any question we give you, except for that extra credit one if we do that some year. But it's kind of crazy sometimes how you have to balance these, but they're a lot of fun. It's like a puzzle. If you guys like Sudoku, it's kind of like a little puzzle. All right. So let's look at this one. This is just more practice, right? So solid calcium metal reacts with water to form an aqueous calcium hydroxide and hydrogen gas. So first of all, we've got to write this out. What does this look like in terms of the formulas? All right, so why don't we pause and practice real quick, and then I'll go through it. All right, first, we get this. Calcium with a little S after it, plus H2O with a little L after it, gives you Ca in parentheses OH2, AQ, that's aqueous, meaning that it's dissolved in water, plus hydrogen gas, has H2 with a G, right, in parentheses after that. Okay, so now we need to balance this, right? So that was writing it out, but now you have to balance it. Yeah, we have to do all of these steps for our questions that we might have on a test. So now we count each number of each of these. So on the reactant side, I have one calcium, two hydrogens, one oxygen. On the product side, I have one calcium, four hydrogens, and two oxygens. So I've got to go through and start making successive passes. So what you can see here is I could probably pretty easily balance this by just putting a 2 in front of my water, because that's going to give me 4 hydrogens, which will balance out what I need on my reactant side, because it also gives me 2 oxygens. And so I can double check that, and I get it. I'm done. That's the kind of stuff we expect you to be able to do. Okay, so if you can't do it, we've got tons and tons and tons of practice problems for you guys to do. And so if this is kind of like, oh man, I need to practice this before I really get it, then just ask me. I can give you lots of practice sheets. Okay. All right, so let's going to practice this one again. This is going to be a pause and practice. I want you to go ahead and balance this one. Ready? Go. And you're back. And this is what you got. Yeah, you're amazing. And we're going to do another one. Ready? Pause it. And we're back. And this is what you got. All right. I know that was in black and you could probably see it the whole time, but I hope you didn't cheat. I hope you didn't look. All right, here we go. Did we do everything we set out to do today? Oh my goodness. I know I went kind of fast, but let's see if we can do what we set out to do. All right. We wanted to identify characteristics of a chemical reaction. All right, things like it releases heat, releases gas, releases light, changes color, things like that. These are the characteristics that will help us to know if a chemical reaction has taken place, right? Identify the parts of and the notation used in chemical equations. So we've learned about things like the arrows and the plus sign and the little element symbols we put on top of the arrows and the little triangle we put on top of the arrows. We learned about the S's and the G's and the L's and the AQs. Make sure to review those if you don't remember them. Can we relate the conservation of mass to the rearrangement of atoms in a chemical equation? Yeah, we sure can, right? We have to balance the equations because we have to show what is happening in nature. We want to show that this is how nature is rearranging the atoms to form new compounds. And so if it has one of this on that side, it's got to have one of that on the other side. It can't all of a sudden go from 2 to 1 or from 2 to 5 or whatever. We have to make sure that the same numbers and types of atoms on both sides of the equation. And then can you interpret a balanced chemical equation for a chemical reaction? Yeah, you can say, you can take the words and write out the formulas, and you can take the formulas and write out the words, right? We've practiced that now. So those are our criteria for success. You can identify the evidences. You can identify reactants, products, states of matter, other common symbols. You can go from word equations to formula and vice versa. You can talk about the law of conservation of mass and why it must be used. And then, of course, you can use the coefficients, not the subscripts, the coefficients to balance equations. All right. I hope you had a good time learning about this stuff. I know it went fast. Hit me up for any extra practice worksheets. Hit me up for any questions. I want to help you guys learn this stuff. And I hope you guys have a great day. God bless you. Be kind to one another.